The transfer area inputs are arguably the most important in cooling tower design. So here we've selected the tower, here we've entered the atmospheric conditions, we've explained in quite detail the dimensions, we've dealt with the operating conditions, and now we're going to look at the transfer areas. Now these are the areas where all the heat and mass transfer is taking place. That is where evaporative cooling is taking place, and these are the areas where the air and water are in direct contact with each other. There are generally 3 areas that we can include in the analysis, and perhaps 4, and these areas are shown by the green circles. So the first area where transfer is taking place, that's in the spray zone. It's indicated by MESP, the Merkel number of the spray zone. Then we can also include the fill, where we have the Merkel number in the fill, and the third area is the Merkel number in the rain zone. We can deselect any of these areas by deselecting these boxes here. So if we don't want to include a rain zone to see what the effect is or any other reason, we can deselect that, and you can see that it's not included in the analysis. Only the areas that are indicated here are included in the analysis. So let's put that one back. We can also include a counterflow rain zone. If we click that, we can see that there's a new dot that appears, and that is the counterflow rain zone. Now we can do that when, for instance, the fill is removed from the cooling tower. We can remove the fill, and then we can just, in the counterflow rain zone, the height of that, we can enter the height. This must then be the same as the one we've entered in the beginning, and we can then replace the fill with the counterflow rain zone. There are a couple of options in specifying the fill, spray zone and rain zone characteristics. So if we select it, it will by default use an empirical equation, but if we know for whatever reason what the Merkel number per unit height of a specific area is, we can deselect that and we can enter this will become active, and we can enter the Merkel number per unit length or Merkel number per meter, or if we click that, it will use an empirical equation. Now the empirical equation for the spray zone is built into the software. The empirical equation for the rain zone is also built into the software, but if you want to bypass that built-in empirical equation, we can deselect it and we can enter an appropriate number for the Merkel number for the rain zone. Specifying the fill is a bit more involved. So if we activated the fill and we've clicked that it must use an empirical equation, you must take note of what is happening in this block. If it says specify parameters, then you've got the specific parameters for that fill handy, and you go to the fill specification tab. You can click on it and you can select an equation. That's the Merkel number per meter height of the fill, and you find these coefficients from fill manufacturers, or you can send the fill away to a fill testing facility like at the University of Stellenbosch in South Africa, where they will conduct a fill test on a specific fill, and they will send you the coefficients and an equation that you need to use together with those coefficients. Or there's also a database included in the software where you can select the fill from a database. So if you click let's use film type from database, you can select a fill number. By selecting the fill type from a database, you can select the fill number and it will tell you which fill you selected. Now to access the database, you can go to the fill numbers, and there are currently 3 different sources that we have for the fills. So the first one is from Lowe and Christie. The second set of fills, that's from a EPRI report, and the third set is from Brentwood. Now, if you go the fill type, this is the number you select in this box over here. So if we select, for instance, 64, it will tell you that it's the Brentwood Shockwave. It's the Brentwood Shockwave, and if you go to figure number, it will show you how that fill looks like. So if you go to fill figures, we know that we have to look at figure 28. We go to the Brentwood fills, we go to figure 28, and that is the Brentwood Shockwave fill that we've selected. If you use the software in verification mode, you just need to make sure that the height of fill that you selected is available. So if you go to the fill type numbers for the Shockwave fill that we've selected here, we can see that it can only be installed in the cooling tower at 300 millimeter intervals. So you have to go to the dimensions and then enter a fill height that is a multiple of 0.3 meters or 300 millimeters. It is also possible to install a second fill in the cooling tower, and you can do that by click on use second fill in the multi-fill input box. So if we select include second fill, we can also select a fill number for the second fill. So if we do, for instance, putting fill type 1, and we can specify a height for that second fill height. If we do it 0.5 meters, you can see that it will enter a second fill in the figure, so that you can verify that this is what you intended to be, because some cooling tower manufacturers have a film fill and above it they have a splash fill, for instance, and then you can include that second fill here. Just something to remember, that the fill height that you enter in dimensions here, the LFI, that is the combined fill height of the first and second fill, as you can see in the dimensions over here. So just make sure that your second fill height is entered correctly, and it will give you the first fill height in meters just below it, and these heights must be such that the fills that you selected are available in those heights. The last input in this screen that we have to discuss is the model selection. Now there are 3 models available in the software. It's the Merkel model, the Popper model, and the E/U model. Now the Merkel model is the most commonly used model in cooling tower analysis, and you have to use the same model here as the model that was used when the fill characteristics were determined. However, you can use other models, but then you have to sometimes, especially for the Popper model, you have to change the adjustment factor. So if you select the Popper model and your fill is based on the Merkel method, you have to change the adjustment factor to 1.07 to 1.09. That is typical adjustment factor if you want to use the Popper the Popper transfer method. Now you would generally use the Popper transfer method if you are very interested in the outlet conditions of the air, because the Merkel method does make some simplifying assumptions, and the major assumption there is that the air that leaves the tower is saturated with water vapor. Now it's not a very bad assumption, but if you are in very dry regions or you are in very humid regions, then the outlet air might be unsaturated, or it might be supersaturated depending on the conditions. And then if you solve the cooling tower with the popper method, it will give you a much more accurate view of the conditions of the outlet air. But generally we'll use the Merkel method with an adjustment factor of 1. The number of levels is not applicable to the Merkel method, but as soon as you use the popper method, you have to supply the number of levels, which usually anything between 5 or 10 should be satisfactory. The Merkel method and ENTU methods are based on the same simplifying assumptions, whereas the popper method is not based on those assumptions. It is therefore the more rigorous approach and generally takes longer to solve than the other two methods. I'll explain the differences between the Merkel and popper methods by way of example in a different video.